Let's begin. We begin, as the worksheet does, with the not. Now, we'll explain what that is. Another way of understanding it is the inverter. And that is a concept that we will have already come across in some of the processes related to the 1's complement and 2's complement. When we had to find these 1 complement and 2's complement, we had to invert a binary value and create this 1's complement. So we've already seen mathematically a use for not, but what we'd like to do in this very short video is spell out some of the relationships and some of the concepts associated. We begin with a little bit of what you might call mathematics. If we have an original value, let's go in reverse order to how I've presented it in the worksheet. So imagine I have an input value and I have a column there for that, and I have an output which I'm going to call x. If my input is 0 and my input is 1, for each of these values I have a corresponding output. So for 0 the output is 1, and for 1 it's 0, because the not operation takes a value and inverts it. Okay, so that's what this table represents. If that's your input, that's the corresponding column for output. That's the first thing to note. Second thing is the gate. So in computer systems, let's use a different color, we represent this operation with a triangle with a little tiny circle at the tip of the nose. And we write it like this. So there is our A, our input, and there is our output, x. So just as we had in the previous slide, if A equals 0, it goes through, it's reversed, and it comes out to 1. If the input is 1, it goes into the NOT gate, goes through the inversion process, and it's 0. So that is how, in computer gate, what's called a logic gate. So let's just write that term down so you know this thing here is called a logic gate. And it represents a physical process in the computer system. It can also represent a piece of software. Finally, we come to the algebra. And this is the one bit that some people who are unfamiliar might struggle a little bit, but it's very important that you understand this as well. So we said if your input is A, and then we invert it. So how do we represent that with algebra? Well, there are two symbols. One is you put an apostrophe. So when you have a value, which could be a 1 or a 0, so this is algebra. Think of this letter A as your input value. It could hold 0 or 1. This little apostrophe next to it means that whatever value it had, it's being inverted. And its result is stored in your output value, x. Another way of representing the in process of inversion is there's your value and you put a bar across the top. And then that gives you your output value. Now that's the mathematics way of representing what we've shown in the previous two slides. And what I would recommend is that you do not dismiss this, because it's very, very crucial later on, especially if you're aiming to get a good grasp of the whole territory. So finally, let's put it to some kind of use. We had in previous slides the idea of 1's complement. And if you remember, 1's complement simply reverses or inverts the value. So imagine I have a binary value 1, 1, 0, 1, 0. In computer terms, this, let's use a different color so we can just make this clear, right? So there's your values. For the actual gate, involved, let's use a different color. So we're going to point the triangle downwards, so the output comes down here, right? So it's going to input into here, into a NOT gate. It's going to come down here. It's going to input into a NOT gate, come down here. You may remember in the original videos, there was no real image of what happened in the computer system. So let's have a look what I've just done here. That's your original binary number. So each value goes through the NOT gate and is outputted one by one, and the inverse or the complement will come out the other end. So let's use a different color, and we'll start with the one to the right. So 0 turns to 1, 1 turns to 0, 0 turns to 1, to 0, and to 0. And that is the most familiar place that a NOT gate is operating. And notice here, I have 1, 2, 3, 4, 5. 5 in a row, so I can build a piece of hardware, I can store these and pass these values in simultaneously. Now here's an important observation. We have 5 pieces of information here, 5 digits, so this is a 5-bit binary number. Okay. There's different vocabulary connected to this, but the crucial element is this notion of 5-bit, because that will come back again and again. And notice that if it's 5-bit coming in, it's 5-bit coming out. Now these are actually, in real life, going to be translated into pieces of hardware. So you can't add another one. And when you think back over adding and all the processes we want, sometimes we had values which spilt over when we were adding 2 binary numbers. This is part of the reason that that overflow or things that spill over aren't easy to deal with computer systems. So we have 5 NOT gates for 5-bit number, and there's the output.